last class we looked at kinematic pairs, and we will continue with. So, a kinematic chain is made up of links connected by kinematic pairs essentially. So, links are the rigid bodies, and the points of attachment to other links are called nodes. So, nodes are the points of attachment to other links. If a link is only connected to one other link, so say you have a link that is only connected. So, link 2 is an example of a singular link, it is attached to only one other link. Okay. So, here you can see here is a link which has 4 attachments. So, it has 4 nodes, this link has 3 nodes. So, links can also be classified based on the attachments to the other links. So, singular link attached to one other link, a binary link which you will find to be one of the most common is attached to, it has 2 points of attachment. So, links may be shaped, in real life links may have complex shape, but as far as the kinematics are concerned, we are only concerned with how they are attached to other links. So, a binary link would typically be represented like this. So, binary link which has which is connected to 2 other links by revolute joints would be represented like this. So, it has 2 nodes, 2 points of. A ternary link similarly has 3 nodes, quaternary 4 nodes, and so on. So, if you have a block that is sliding with respect to one link and is attached to another link through a revolute joint, the block is still called a binary link. It has 2 points of attachment. One is the prismatic pair, one is the revolute pair. So, 2 is still a binary link. So, in a kinematic diagram this would be a binary link. A ternary link would be represented in the following ways. So, you could have this, and you have typically have to show when you want to indicate it is a single link, you either show it in terms of welds or you shade the entire link. We will see later why it is not always necessary in the case of a triangular link like this, but this is especially important if you have a ternary link like this. You would normally interpret this as 2 binary links unless it has this weld. In that case it could be like this or like this. So, it has to have that weld to show that it is part, the nodes could be on the same line. Okay. This is different from, this is 2 binary links. If the weld is not present, it is interpreted as 2 binary links. These kind of links, a ternary link without all 3 nodes on the same line can also be represented like this. Okay. So, these are simplified representations of links for the purpose of kinematic diagrams. Similarly, a quaternary link, maybe if I want to show a quaternary link, I would have to show, in this case it is especially important because otherwise it could be represented, it could be mistaken for a 4 bar linkage. Okay. So, these are the link representations that we will use in simplified diagrams. Actual shapes of links could be considerably different. So, you can see here this is a mechanism. First of all, a lot of the things that we are doing initially in the first part of the course or in the majority of the course will be planar mechanisms, where all the points on the mechanisms move in parallel planes. So, I can have most real life mechanisms will have a 3D configuration, okay, because you need to be able to take loads in all directions. So, you will rarely find mechanisms that are in a single plane. Even if you look at a folding chair, you will have the same mechanism duplicated on the other side, right, with a common joint. So, here if you look at this, all these links, this link, this link, this link and this link. So, there are 4 links here. They are all what kind of links? Binary links. You can see that this one has 2 nodes, similarly this, but their shapes are considerably different. But if I draw a simplified representation, all I would do is just use the nodes basically and draw it as, in this case, this would be my mechanism, say this is the fixed link. Okay, so, that would be the representation of this mechanism, but every point regardless of its shape, okay, on the link, every point on every link will move in parallel planes as the mechanism moves. That is what makes this a planar mechanisms, and therefore, you will only count the links in the plane. You are not going to be counting these extra links because that will so, the only thing responsible for the kinematics of this mechanism in the plane is this set of links. So, you only call this a 4 bar. So, the kinematic diagram is basically a simplified representation. So, here is, it is similar to what I showed you here, a real life mechanism that has links of various shapes. And so, if I want to draw the kinematic diagram of this, so in this case, since you should all be familiar with this, I will just go ahead and do it. So, you will represent the fixed pivot like this. Then my first link, even though it is a circle here, the node, it is a binary link, the node is here. So, I would just represent it in that fashion. And then the next node is here. So, this is my link, and then this is another fixed pivot, and this is my 4th link. Okay. The fixed link is designated 1 usually. So, 1, 2, 3, 4, I have 4 links, and typically if you have a point of interest, okay, if you are interested. So, for instance, this mechanism is used to advance a film strip. So, it is a 4 bar linkage, but really the point of interest is this point C, okay, because you are interested in the path that it follows. Okay. In this case, what it does is you have the earlier movies used to have these film strips which will have the holes. Okay. So, this mechanism, as this rotates, it will latch on to the hole here, pull it down and come out of it, and then go, and so it will advance the mechanism in that, it will advance the film strip in that fashion. Okay. So, since this is a point of interest, typically in the kinematic diagram you would also show the point of interest, but to indicate that it is not a link, again you will show that it is part of link 3, you will show it in that fashion. And you also do not put an open circle there, because that would indicate a node for a revolute joint. So, this is the proper way to draw a kinematic diagram. So, you draw the revolute joints. Okay. So, basically kinematic chains are constructed by connecting links with kinematic pairs, and you could have an open kinematic link, okay, or a closed open kinematic chain or a closed kinematic chain. Closed kinematic chain, every link will be connected to at least 2 other links. Okay, that is what distinct. So, there will be no singular link. In an open chain, as we will see here, you will see that there are 2 singular links here. Okay. So, if I take apart a 4 bar and just leave it, that would become an open kinematic chain. So, a closed kinematic chain will have every link. So, there will be no singular links in a closed kinematic chain. Okay. So, and for a lot of analysis, if you consider a chain that contains only binary links, we call it a simple chain. Okay. If it has so for a slider crank, so this is your typical 4 bar kinematic chain, and a closed kinematic chain becomes a mechanism when you fix one of the links in the kinematic chain. When you fix one of the links, then you can constrain, then it becomes constrained motion between some input and some output. One or more inputs can be more than one for a single output. Okay. So, so this is called a 4R kinematic chain. You have 4 revolute joints in this kinematic chain. This would be called a 3R 1P. There are 3 revolute joints and 1 prismatic joint. In a compound kinematic chain, closed kinematic chain, you would have links that are higher than binary links as well. If it is only binary links, if it is a singular if it is a kinematic chain with a singular link, it is not even a closed kinematic chain. Only binary links, it is a simple chain. More than binary links, it becomes a compound closed chain. So, the third example there is a compound closed chain. This is your, these are examples of open kinematic chains. So, a closed kinematic chain with one link fixed forms a mechanism. So, in a 4 bar mechanism, which is one of the most common mechanisms we will encounter, the fixed link is called the frame, your input is typically called the crank. So, the input can be, so the crank can sometimes be used to refer to a link that can make a complete revolution, or sometimes it is used to refer to the input link as well, okay, whether or not it can make a complete and the output is usually called the follower, and the link. So, the crank and the follower are both fixed, pivoting about points fixed to the ground. Okay. In the case of the coupler, this is a floating link. We call this a floating link, and it is the link that connects the crank and the follower, the input link in the 4 bar. Well, I should not say input link, because sometimes you could have a mechanism that has the coupler as the input link. This mechanism here, it is what is known as an inline or a central slider crank. So, this is the 4 bar is typically referred to as a 4R mechanism, 3R 1P is your slider crank. Okay. So, again you have the frame, one link which is fixed, then you have a crank, you have a coupler or connecting rod, and you have the follower in the case of the slider crank is your slider block. Okay. And if the rotation of the crank is in line with the path of the slider, then it is called an inline or a central slider crank. If the two are offset, if the path of the slider is offset from the point of rotation of the crank, then this is called an offset slider crank, offset or eccentric slider crank. Okay. Again this is the crank, coupler and the slider block. We will move on to the mobility criterion. So, you have a set of links connected by joints. Okay. You know what the connectivity of the individual joints are. For this system, for this kinematic chain that you have created, for the mechanism that you have created by fixing one link in the kinematic chain, how do we predict the mobility of the mechanism? So, let us look at the planar mobility criterion. If I have one link moving in the plane, okay, to completely specify the motion of that link, how many degrees of freedom do I need? One link moving in the plane. I have a link moving in the plane. I need how many degrees of freedom? 3 degrees of freedom, because I need the x and y coordinates of one point and the orientation of one link in the plane. Typically that is what I need for that. What if I take these two coordinates x1 y1, x2 y2? There is a constraint. So, I have 4 quantities, but the distance between those 2 points remains the same. That is a constraint on the link. So, again I only need 3 independent quantities to specify the location of the link. So, one link moving in the plane has 3 degrees of freedom. Now, my kinematic chain, okay, first before I make the chain even, I take n links, okay, and independently if I have these n links moving in the plane, how many degrees of freedom will I have? 3n. For my system I have 3n degrees of freedom. Now, I start connecting the links by joints. Okay. So, suppose I connect the link by a joint which is a single degree of freedom joint. Okay. The joint allows only 1 degree of freedom, which means it is taken away to, okay, before that, in a mechanism I have to fix one link. So, once that link is fixed, it loses all its degrees of freedom. So, if I start looking at the mobility of the mechanism, I had 3n, now because I have fixed one link, I have 3 into n minus 1. Okay. Now, for every joint that I had, every single degree of freedom joint that I add to the mechanism, I am taking away 2 degrees of freedom, okay, because the joint will only allow 1 degree of freedom. So, that is how I get the 2J1 single degree of freedom joints. And then if I add some 2 degree of freedom joints, like say a cam joint, okay, then that will take away only 1 degree of freedom, because the cam joint allows 2 degrees of freedom. I can have sliding and rolling. So, this is how I get the mobility criterion, which is called the Kurzbach's mobility criterion. And this is the planar mobility criterion. We will come to the spatial criterion later, because we are assuming, because we are starting off by assuming that it has only 3 degrees of freedom in the plane. Okay. So, now if we look at some common examples, first let us start off with the 4 bar. Okay. So, I have the fixed link as 1, I do the kinematic diagram 3 and 4, 1, 2, 3 and 4 links. Now, each 1 degree of freedom joint I designate with a say tick mark. So, there is 1 between 1 and 2, 2 and 3, 3 and 4 and 4 and 1. So, my n equals 4, J1 equals 4. So, my mobility is equal to 1. Similarly, for a slider crank, it is no different because the 4th joint is still a safe freedom joint, the planar joint. So, I still have m equal to 1 for the slider crank. Suppose I only connect 3 links, 1, 2, 3, say 1 is fixed. I have, what do I get for this mobility? I get 0. Mobility equal to 0 for this mechanism implies that it is a structure. So, it cannot, the links cannot move with respect to one another. Okay. So, that is why for a ternary link, even if I just indicate as 3 links, it does not matter, because it is already a structure, there can be no relative motion between the links. But it is good practice for you to either shade it or use the welds. Okay. Same 4 bar, if I add another link like this. Okay, I have 1, 2, 3, 4, I add a 5th link there. What happens to it? I have n equal to 5, joints 1, here how many joints do I count? There is a joint between 2 and 3 and between 2 and 5. So, I have to count, make sure I count 2 joints there. Here there is 1, here again I have 2 joints. So, if you have p links meeting at a single joint, you would count p minus 1 joints there. Okay. So, you have to make sure that you get the right amount of joints. So, J1 is 1, 2, 3, 4, 5, 6 and you get mobility equal to 0. If I add one more link, okay, then I will get I will actually get mobility equal to minus 1. So, say I add another link like this, I will get mobility is minus 1. So, this indicates that it is a statically indeterminate structure. So, mobility greater than 1 implies it is a mechanism mobility equal to 0 implies it is a structure, mobility less than 0 implies it is a statically indeterminate structure. So, you need more than the static equations of equilibrium to solve for such a system. So, again all of these you would first do the kinematic diagram, and this is nothing but you can see it is only a 4 bar. So, obviously its mobility will be 1. Okay. Is not very sensitive. So, excuse my drawing because it is not letting me erase part of the line this. But if I have a folding chair which has a pin that is attached to the seat, okay, that can slide in the slot in this backrest link, okay, what would be my mobility? So, let us consider, say this link, I fix this link. Okay. Usually when you hold the chair and then you try to fold it. So, I would have this would be link 1, link 2, link 3. Okay. The joints, this would be a revolute joint, and this would be what kind of a joint? 1 degree of freedom or 2 degrees of freedom? It is a 2 degree of freedom. It is that pin in a slot. It can both slide, it can rotate as well as slide. It can be replaced, you can add another link to make it all lower pairs, but the way it stands, this is a 2 degree of freedom joint. So, say you denote that by Nx. So, now you have n equal to 3, J1 equal to 2, J2 equal to 1. So, what is my mobility? So, I get a single degree of freedom mechanism. Okay. So, you need to be able to recognize the connectivity of the joint correctly. The pin in the slot is something that throws most people off, that is why I did this example. Okay, that is a joint with 2 degrees of freedom. For most planar linkages, the joints that you are going to encounter are your revolute pair, prismatic pair, rolling or a cam pair. Okay. Planar you can think of as prismatic plus rotation, like in your drafter, right there. These are the joints that you will encounter in planar mechanisms, because for instance a screw pair, the rotation is happening about one axis, but the translation happens about is observable from a different plane. Okay. So, if I place the screw joint like this, I am not going to be able to see the translation, I can only see the rotation. Similarly, if I am looking at only the translation, I can't see the rotation from that same plane of observation, are not part of a planar mechanism. You will find screw joints in many applications, but they will be used for things like a one time adjustment. So, if you look at a pair of pliers, cutting pliers, right. Many of them will have a screw joint at. So, the pliers, if you look at it, it is essentially a 4 bar linkage, but you will have one screw joint here which will basically adjust one of the fixed pivots. So, it can change how it grips, the gripping. So, that screw joint you would not consider as part of the mechanism itself, okay. That is a separate thing that is used only to adjust this planar mechanism. So, even though the joint exists in the planar mechanism, it is not part of the kinematics of that 4 bar. So, you have to be able to differentiate between which joints belong to the mechanism that you are analyzing. Okay. So, now let us look at exceptions to the mobility criterion. So, as with any rule, there are exceptions. So, if you look at say I construct a mechanism like this. Can you tell me what its mobility will be? I will get a mobility of n equal to 5, j1 equal to 6, I will get a mobility of 0. Okay, that means it is a structure. Now, suppose I change the form. So, I make these links equal. Okay, I change the form of the mechanism. I make these links equal. This would be one link. Now, what happens? I can actually move this mechanism, right. The mobility equation still tells me that the mobility of this is 0, but actual mobility equals 1 for this mechanism. Okay. The reason for that is the mobility criterion does not, and that is possible with this mechanism, a mechanism of a mobility of 1 is possible only because of the geometry, the special geometry of this mechanism, because all the links are equal. Okay. So, if there are special geometry considerations, you will find that sometimes the mobility criterion will not apply. Okay. So, you will have, similarly you have two friction discs. Okay. You have say a rolling contact. Okay. Here, if you use the mobility equation, what happens? What does it predict the mobility to be? Predicted m will be 0, but you know that this friction can transmit motion to the other disc, its actual mobility is 1. Again, it does not take into the fact that the way these discs are located, the geometry is what is responsible for the actual mobility. So, actual mobility equal to 1. So, there may be exceptions to the mobility criterion. Sometimes you could have a predicted mobility that is greater than 1. So, say you have a cam, okay, and say I put a follower, a rocking follower like this, okay. Then I have 1, 2, 3. So, I have a cam pair here. I get a mobility of 1. for this. Suppose the same thing I change the structure. So, you know, I do not want too much wear on just one part of this follower. Okay. So, I modify that to say that I am going to have a roller here instead of just this link directly in contact with the cam, okay, because the roller will keep spinning and I will have different points of contact. So, practically that is a better way to handle wear. So, in this case 1, 2, 3, 4, I have 1, I have that, this and this. What is my mobility here? I have n equal to 4, j1 equal to 3, j2 equal to 1, gives me a mobility of 2. Just plug it in, 9 minus 6 minus 1, I get a mobility of 2. It is pretty much the same. If you look at the input and output, you will get the same result in the output. So, if I move this cam, this predictable motion of the output link here. So, what is this additional mobility that we have here? It is the angle of the roller about that, which for your practical application does not matter, but it is an existing degree of freedom in the mechanism. So, mobility basically tells you how many inputs do you need to get your predictable output. So, if a mechanism has mobility equal to 1, it means one input will give you a predictable output. Here this mobility equal to 2 tells me that I have to give 2 inputs, but it turns out that is not really true. I do not need to give an input to the roller, right, because it does not matter. I mean the roller has a degree. So, this is still the actual mobility of this mechanism is still 1. With one input to the cam, I get a predictable output of the follower. The additional degree of freedom does not really matter to me. Okay. So, when you have degrees of freedom like that, which is encountered typically with rollers and things like that, those are called idle degrees of freedom, because they do not contribute to the input output relationship, they do not affect the input output relationship. So, any degrees of freedom that do not affect the input output relationship are called idle degrees of freedom, and they will give you, they will over predict the mobility of the mechanism. So, in some cases, in this case the mobility was under predicted for this, because the actual mobility is 1, the equation tells you it is 0. In this case the equation tells you it is 2 when the actual mobility is still 1. So, you have to be careful to see actually what is happening with the mechanism. So, the mobility criterion is a first check on how things are going to move, but then you would have to actually look at how things are. So, now let us do a few things with the mobility equation. Okay. So, you can represent any linkage. So, if a mechanism has only lower pairs, we typically call it a linkage. We call it a mechanism, it is called a more general, more generally it is referred to as a mechanism if it also has higher pairs in the kinematic chain, but if we are only using lower pairs, we tend to call it a linkage. And even in a linkage, you can always represent any linkage as a kinematic chain which has only links and simple hinge joint. So, a simple hinge joint is a revolute joint that connects only 2 links. Okay. So, it does not say that the links have to be binary. Okay, it only tells you that. So, so for instance, instead of creating a mechanism, if I have a mechanism like this, if I want to represent this only with simple hinge joints. So, this is a 6 bar mechanism. Okay, I have not put a weld here. Okay, so, that is, these are separate links 1, 2, 3, 4, 5, 6. You will find that it has mobility equal to 1. This is a 6 bar mechanism. I want to represent this with only simple hinge joints, then what I would have to do, see here I have what is known as a, this is a multiple joint. I should not circle this. I have 3 links coming together at this joint. So, when I do my mobility calculation, I would count 2 links here. Okay. I do not want to do that, I want it to have only simple hinge joints, in which case I would redo this mechanism as, this is what I would do. I would convert this into a ternary link. So, that now all my hinge joints are simple hinge joints. Okay. So, I convert out of these 3 binary links, I convert one into a ternary link, so that I have only simple hinge joints. The reason I am doing this is because we will now do some things with the mobility equation, where we make the assumption that we are converting any mechanism in any linkage into something with only simple hinge joints. Okay. So, we will do that. So, we take the mobility criterion, we see the, so if I am only dealing with simple hinge joints, I can write the mobility criterion as 3 into n minus 1 minus 2 j1. Okay. I am saying I do not have any 2 degree of freedom joints in the mechanism. Now, let us say that, so if n is my total number of links, let n2, it is a closed chain. So, I do not have any links that are singular links. So, n2 be the number of binary links, n3 be the number of ternary links, and so on. So, ni is number of links with I nodes. Okay. Each of those links has I nodes. Okay. And I am considering that all these nodes have hinge joints. Okay. Let us say they have simple hinge joints. So, I can write my mobility equation as, so if this is the case, then what is my J1? I can express J1, each simple hinge connects 2 links. Okay. So, my J1 will be half of two n2 plus 3 n3 plus I ni. Okay, because a binary link will connect to 2 other links. So, when I count the joints, I will get, this will be the total number of joints. So, now let me just n equal to n2 plus n3 plus ni, I have J1 equal to half of 2 n2 plus 3 n3 plus I ni. Okay. So, this gives me m equal to, I can write in this form 3 into minus 1 minus 2j1. So, I get 2n2 plus 3n3 plus ini. So, what do I get? Okay. So, this is the now for a mechanism to have mobility 1, which is the most practical application. You have one input, you want a predictable output. I can write the original mobility equation as 1 equal to 3 into n minus 1 minus 2j1. So, I get 3n equal to 4 plus 2j1. Did I do that right? No. 3n minus 3. Yeah. So, 3n equal to 2j1 plus 4. So, first off, this tells me j1 is an integer. Okay. So, this tells me that, so what kind of a number will this be? If it is a valid linkage, this is going to be an even number. Two j1 plus 4 is an even number, which means n has to be even. Okay. This 3n equal to 2j1 plus 4 is called Grubler's criterion. So, the first thing that we see from this Grubler's criterion is, if you want a mechanism with mobility 1, the number of links have to be even. Okay.